The directions say to determine whether the given differential equation is exact. If it is exact, solve it. Let's take a look at example 1. Suppose we're given 2x minus 1 dx plus 3y plus 7 dy is equal to 0. So we're going to first determine whether this differential equation is exact. Let m of xy equal 2x minus 1. N of xy equal 3y plus 7. The partial of m with respect to y is equal to 0. The partial of n with respect to x is equal to 0. Since the partial of m with respect to y is equal to the partial of n with respect to x, this differential equation is exact. Now, to determine the solution, what we do first is set the partial of f with respect to x equal to 2x minus 1. We want to note y is fixed. Step 2. We're going to essentially take the partial integral with respect to x. And with y fixed, this is what it looks like. We get f of xy equals x squared minus x plus g of y. The partial of f with respect to y, this is step 3, is equal to g prime of y. Now, we set the partial of f with respect to x equal to essentially m of xy. That's going to determine f of xy. Then we're going to set the partial of f with respect to y equal to n of xy to get a handle on g of y. And this is going to be the pattern for the next 3 examples. So I set g prime of y equal to 3y plus 7. So g of y is equal to 3 halves y squared plus 7y plus c. And putting it all together, we have f of xy equals x squared minus x plus 3 halves y squared plus 7y plus c. So the solution of the differential equation is x squared minus x plus 3 halves y squared plus 7y plus c is equal to 0. And you might find in the book that they have the c on the right side of this equation, and that's okay, and I would call that equivalent. That's example 1. Example 2. Suppose we have 5x plus 4y dx plus 4x minus 8y cubed dy is equal to 0. Let m of xy equal 5x plus 4y and let n of xy equal 4x minus 8y cubed. The partial of m with respect to y is equal to 4. The partial of n with respect to x is equal to 4. Since the partial of m with respect to y is equal to the partial of n with respect to x, this differential equation is exact. Now let's go after the solution. Set the partial of f with respect to x equal to 5x plus 4y. Again, I want to note y is fixed. Now we're going to take the partial integral of f with respect to x. And when we do that, we get f of xy equals 5 halves x squared plus 4xy plus g of y. Remember, y is fixed, so g of y is fixed. So from here, we're going to take the partial of f with respect to y, and when we do that, we get 4x plus g prime of y. And so we're going to set 4x plus g prime of y essentially equal to n of xy, and what we're going to do is try to get a handle on this g of y. So in other words, 4x plus g prime of y is equal to 4x minus 8y cubed. The 4x's cancel, and we get g prime of y equals negative 8y cubed. And so what that tells me is that g of y is equal to negative 2y to the 4th plus k. Remember, k is constant. Putting it all together, we get f of xy equals 5 halves x squared plus 4xy minus 2y to the 4th plus k. Setting f of xy equal to 0, the solution of the differential equation is 5/2 x squared plus 4xy minus 2y to the fourth plus k equals 0. And if you guys have had Calculus 3, in Calculus 3 you learn how to determine whether a vector field is conservative. And if it's conservative, you find a potential function little f such that capital F, the vector field, is equal to the gradient of some small f. And that the process for doing that is very similar to the process for finding the solution to an exact differential equation. Those processes are very similar. Okay, let's take a look at example 3. Suppose I have 3x squared y plus e to the y dx plus x cubed plus x e to the y minus 2y dy is equal to 0. Let m of xy equal 3x squared y plus e to the y, and let n of xy equal x cubed plus x e to the y minus 2y. The partial of m with respect to y is 3x squared plus e to the y. The partial of n with respect to x is 3x squared plus e to the y. Since the partial of m with respect to y is equal to the partial of n with respect to x, this differential equation is exact. Okay, so from here, we're going to set the partial of f with respect to x equal to 3x squared y plus e to the y. Y is fixed. So f of xy equals x cubed y plus x e to the y plus g of y. So the partial of f with respect to y is x cubed plus x e to the y plus g prime of y. So we're going to set x cubed plus x e to the y plus g prime of y equal to x cubed plus x e to the y minus 2y. Well, that says g prime of y is equal to negative 2y. So g of y is negative y squared plus k. K is constant. And so f of xy equals x cubed y plus x e to the y minus y squared plus k. And so setting f of xy equal to 0, the solution of the differential equation is x cubed y plus x e to the y minus y squared plus k equals 0. Let's take a look at example 4. Suppose we are given 1 plus the natural log of x plus y over x dx equals 1 minus the natural log of x dy. The differential equation needs to be in the form m dx plus n dy equals 0. So if we want to determine whether or not a differential equation is exact, we must have it in this form. So if you go back to these previous examples, notice how we have essentially m dx plus n dy equals 0. That's example 3. In example 2, we have, again, m dx plus n dy equals 0. In example 1, we have, again, m dx plus n dy equals 0. The first 3 examples were in that form. We need to make sure example 4 is of that form as well. And right now, it is not. And so what we want to do is we want to move 1 minus natural log of x dy over to the left-hand side. And when we do that, we get 1 plus the natural log of x plus y over x dx minus the quantity 1 minus natural log of x dy equals 0. Still not enough because we need to distribute the negative inside to each term. And when we do that, we get 1 plus the natural log of x plus y over x dx plus the natural log of x minus 1 dy is equal to 0. And now we're ready to determine whether or not this differential equation is exact. And then B, if it is exact, we get to then find the solution. We get to solve it. So we're going to let m of xy equal 1 plus the natural log of x plus y over x. And we're going to let n of xy equal to natural log of x minus 1. So the partial of m with respect to y is equal to 1 over x, and the partial of n with respect to x is 1 over x. Since the partial of m with respect to y is equal to the partial of n with respect to x, this differential equation is exact. Let's find the solution. Set the partial of f with respect to x equal to 1 plus the natural log of x plus y over x. Y is fixed, so f of xy is equal to x plus x times the natural log of x minus x. I claim that's the integral of natural log of x with respect to x. You do that by parts. And then, so again, we get x plus x natural log of x minus x plus y times the natural log of x plus g of y. The x terms are going to go away, and we get x natural log of x plus y times the natural log of x plus g of y. And remember, we want to get a handle on that g of y. So the partial of f with respect to y is equal to natural log of x plus g prime of y. Set the natural log of x plus g prime of y equal to the natural log of x minus 1. And so g prime of y equals negative 1. So g of y is negative y plus k. And if we put that all together, we get f of xy is equal to x natural log of x plus y times the natural log of x minus y plus k. So the solution of the differential equation is x natural log of x plus y natural log of x minus y plus k. And I want to just discuss one more example, if we don't mind. This is on example 5, and suppose I give you the following. Suppose I give you 5y minus 2x y prime minus 2y is equal to 0. Remember that y prime is dy dx. And so I can write this as 5y minus 2x dy dx minus 2y is equal to 0. Now, this can be written as 5y minus 2x dy minus 2y dx is equal to 0. But I want to write it in its proper form. Remember, I want to write it as m dx plus n dy is equal to 0. So I'm going to write this as negative 2y dx plus, in parentheses, 5y minus 2x dy is equal to 0. And remember, m of xy is negative 2y, and n of xy is 5y minus 2x. Does it make sense? And so from here, I'm going to take the partial of m with respect to y. And when I do that, I get negative 2. And if I take the partial of n with respect to x, I get negative 2. And so notice how they're the same. Since the partial of m with respect to y is the partial of n with respect to x, this differential equation is exact. And the process for finding the solution remains the same. You know what I mean? So, in other words, when I look at this, I'm going to set the partial of f with respect to x equal to, and I happen to look over here. So I set it equal to negative 2y. So f of xy is negative 2xy plus g of y, right? Same game the whole time. And then I take the partial of f with respect to y. And when I do that, right, I'm going to get negative 2x plus g prime of y. And so I'm going to set negative 2x plus g prime of y equal to essentially n of xy. That's this mess over here. So I'm going to set it equal to 5y minus 2x. So g prime of y is equal to 5y because the negative 2x terms cancel. So g of y is 5 halves y squared plus a constant k. And so therefore f of xy, if we put it all together, right, we get negative 2xy plus 5 halves y squared plus k. And so if I set f of xy equal to 0, the solution of the differential equation is negative 2xy plus 5 halves y squared plus k equals 0. And I do want to stress that if you guys have had a Calculus 3 class and you were trying to find the potential function for some conservative vector field, you're literally going through something really quite similar. You know, yeah. So if you've had Calculus 3, you will see that this is very familiar. And that'll do it for this video. Okay, thank you.